Hello everyone. Today we are going to look at the paper presentation on training language models to follow instructions based on human feedback. And names, as the name of the paper suggests, it's focused on the training the language models to be more human oriented and based on actual human feedback. So I'll give you quickly a brief of the paper. The paper found that simply making AI models bigger doesn't make them better at following instructions. In fact, massive models like GPT-3 often produce unhelpful or toxic responses because they are only trained to predict the next word on the internet. To solve this, the authors created Instruct GPT using the RLHF, which stand for Reinforcement Learning from Human Feedback, for which they hired people to provide demonstration and rank the AI answers. This coaching taught the model to align with the human intent, and these results were pretty good compared to the GPT, and it's 100 times smaller than the GPT-3 and very much preferred by the human users. The Instruct GPT is more truthful, follows rules better, and it's less toxic. By blending human feedback with original data, the team avoided performance losses. This works prove that human guidance is most cost-effective way to build the helpful AI. As we can also see, the Instruct GPT has only 1.3 billion parameters compared to 175 billion parameters of the GPT-3, which is 100 times productions. So it's cost effective and very much preferred by the human users. So what's RLHF? So RLHF stands for Reinforcement Learning from Human Feedback, and it is the core idea behind this entire paper. To understand why RLHF is needed, we first need to look at how traditional language models are trained. Most language models like GPT-3 are trained using very simple objective, predicting the next word in a sentence based on the massive internet data. So while this makes them very good at generating fluent and natural sounding text, it does not guarantee that the output is actually useful or aligned with what the user wants, sometimes toxic as well. For example, the model might generate something that is factually incorrect, irrelevant, or even harmful to some. So this is where RLHF comes in. The idea is to bring humans directly into the training loop, and instead of learning from the raw text, the model also learns from the human preferences. So humans look at the different responses generated by the model and decide which one is better. For example, which answer is more has helpful, more accurate, or safer. So this feedback is then converted into reward signal. Using the reinforcement learning, the model is trained to maximize this reward. So in this, instead of just predicting the next word, it learns to generate responses that humans actually prefer. So in simple terms, RLHF shifts the goal from predicting text to behaving correctly. And this is what makes more model more helpful, more honest, and more aligned with the human expectations. So coming to the main goals of this paper, the goal of this paper is to improve how well language models aligns with the user intent. Even though models like GPT-3 are very powerful, they often fail in the practical scenarios. They might misunderstand instructions, give irrelevant answers, or generate misleading information. So the authors focus on improving three key aspects: helpfulness, honesty, and harmlessness. Helpfulness means the model should actually solve the user task and follow instructions properly. Honesty means it should not make up facts or give false information. And harmless means it should avoid generating toxic, biased, or unsafe content. So, for example, it's my own personal experience. Sometimes when I chat with the chat GPT, it generally gives me false answers, like something, the concept I know, but it gives me answers which are factually incorrect. So I have to correct it. And sometimes it's also start arguing with me that the logic it gives is correct. So that is basically very much harmful in longer use. Well, another important goal of this paper is efficiency. Traditionally, the approach to improving models has been to make the model bigger, increasing the number of parameters. But this paper challenges the idea. It shows that instead of just scaling up, we can get better results by improving how the model is trained. In fact, one of their key claims is that smaller model trained with RLHF can outperform a much larger model that is not aligned with the user. Finally, they also ensure that these improvements do come at the cost, do not come at the cost of performance on standard NLP tasks. So goal is just not alignment, but alignment without losing the capability. Now, before this work, most language models were trained using a next word prediction objective. This approach works well for learning grammar, structure, language patterns, but it has a major limitation. It does not teach the model to understand the user intent. So, as a result, even very large model can produce outputs that are incorrect, irrelevant, and sometimes harmful as well. So, this problem is often referred to as misalignment. At the same time, the idea of using human feedback is not completely new. RLHF had already been used in other domains like robotics, gaming, and in also self-driving cars. So in those areas, instead of defining a fixed reward function, humans guide the system by providing feedback on its behavior. However, applying this idea to large language model was still relatively unexplored. Most NLP systems relied heavily on supervised learning or predefined data set. So there was a clear gap. So we had powerful models, but not effective way to align them with the human expectations. So this paper builds on previous work and applies RLHF specifically to the language models. The goal of this paper is to bridge this gap and create models that are not just fluent but also useful and safe in real world applications. So you can think of this paper as combining two ideas, large scale language modeling and human feedback to solve this misalignment problem. Now coming to this model overview, this is the entire structure of this paper. So let's break this diagram down by understanding each block. So we start with trained LM, this trained LM. So it stands for trained language model, which is the main model we want to improve. This model generates text responses based on the input prompts. Then we have this reward model shown on the right. So its job is to evaluate the quality of the generated text. It gives a score which represents how good or how preferred the response is according to the human feedback. Now below that we have this frozen language model. So this is basically a reference model that does not change during training. It just helps us compare how much the trained model is deviating from its original behavior. So that's where this scale loss block comes in. So it's check for the KL divergence. It measures the difference between the trained model and the frozen model. So this ensures that while improving, the model doesn't start generating strange or meaningless output. Now both the reward from the reward model, the first reward given from the reward model, and the KL penalty. This is now summed to make this final reward signal. So the final reward signal is passed to the RL update block using the PPO, which updates the model step by step. So overall, each block has a clear role, generation, evaluation, constraint, and optimization, all working together to improve the model safety. Now coming to the training pipeline, now let's understand how the data actually flows through the system step by step. So the first step here, we start with a prompt from the dataset. A human labeler with high, this human labeler is writes a high quality response from that prompt. This data is used to train the model using the supervised learning, which is called a supervised fine tuning on or SFT. And now coming to the second step. So instead of writing answers, we generate multiple outputs from the model for the same prompt. Human then ranks this output based from the best to the worst. The ranking data is used to train the reward model so that it learns how to score different responses based on the human preferences. So, and in the third step, we move to the reinforcement learning. A new prompt is given to the model and it generates a response. So this response is passed to the reward model, which gives a score. So based on this score, the model is updated using PPO to improve its future responses. So this process keeps on repeating, generate, evaluate, update, forming a continuous learning loop. So the key idea is here to instead of directly telling the model that what is correct, we guide it using the human preferences at every step. So as we learned earlier, the SFT is the first step of this RLHF pipeline. So SFT stands for supervised fine tuning. So here what we do is human labelers are asked to write high quality responses from variety of prompts. These responses acts as a demonstration of how the model should behave. Then the model is trained on this data using standard supervised learning. So essentially it learns by imitating those human written examples. So this step is very important because it gives the model a strong starting point. Without this, the model would be too unstructured for later reinforcement learning step to work effectively. So at this stage, the model already becomes better at following instructions compared to the original GPT-3. So it learns how format answers properly, stay relevant to the prompt, and avoid obvious mistakes. So it's basically a major step that makes it stand out from the original GPT-3. So, however, there are still some limitations. The model only learns from the exact examples it sees. So it does not fully understand subtle preferences like tone, safety, or what makes one answers better than the other. Also, writing demonstrations for every possible scenario is not scalable because uh, you have to make some person come and give its responses, give his or her responses to every possible prompts. So that is like very tiring. So while supervised fine tuning improves the model significantly, it is still not enough to fully align with human expectations. That's why we move to the next step, where the model learns from the comparisons instead of just examples. Now coming to the second step of the RLHF pipeline. So what it does it instead of asking humans to write answers, we now ask them to compare multiple outputs generated by the model for a given prompt. Like so, the model produces several responses. The human labelers then rank these responses from best to the worst based on criteria like helpfulness, correctness, and safety. So the ranking data is used to train the reward model. The reward model takes a prompt and a response as an input and outputs a single score, which represents how good that response is according to the human preferences. So instead of hard coding rules like this is correct or this is wrong, the system learns preferences directly from the human judgments. So one important advantage of this approach is that it's capture relative quality. It does not just learn what is correct, but what is better compared to other options. So this makes the model more flexible and better aligned with the real world expectations. So the reward model essentially acts as a learned objective functions, which can later optimize using reinforcement learning. So this step transforms the human feedback into something that the model can directly learn from, a numerical reward. So now coming to the final step, reinforcement learning, it is used to improve the model further based on the reward model. The model generates a response for a given prompt, and the reward model evaluates by assigning a score. But this score is now you will be used as a feedback. The model is updated to produce better responses in the future using that feedback. So the specific algorithm used here is PPO or the proximal policy optimizations. So PPO is designed to make subtle updates so the model improves gradually without making the sudden drastic changes. So one important challenge here is that if we only optimize for the reward model, the system might exploit it. For example, it might generate unnatural repetitive outputs to get a high score, but that is not actually helpful. So to prevent this, a KL penalty is added. So this ensures that the updated model stays close to the original supervised model. So there is a balance which is improved based on the human preferences, but don't deviate too much from the natural language behavior. This combination of reward optimization and constraint is what make RLHF very effective. So overall, this step allows the model to continuously improve by learning from feedback rather than just static training data. Now let's look at the data set used in this work. So the data primarily comes from the prompts submitted by the user through the OpenAI API. These are the real world prompts, which makes the dataset very diverse and representative of the actual use cases. In addition to that, human labelers are also created their own prompts. So this helps ensure coverage of different types of tasks and avoid relying on the user data. So the data set is divided into three parts. The first part is used for supervised fine tuning, the second for training, and the third for reward model. The reinforcement learning. So in terms of size, the supervised dataset contains around 13,000 prompts, while the reward model dataset is larger, which is around 33,000 prompts. So these prompts cover a wide range of tasks such as question answering, summarization, brainstorming, chat, and content generation. So most of the data is in English, although the model can still generalize to other language to some extent. So overall, the data set is carefully designed to reflect how people actually interact with the language model, which is important for the real world performance. Now, the human feedback process. So human feedback at its core of this entire approach. So let's understand how it is collected. First, human labelers are trained to follow specific guidelines. So they are instructed to prioritize helpfulness, honesty, and safety while evaluating responses, not their personal agenda. So in supervised fine-tuning stage, they write complete answer from the prompts. And in the reward model stage, they are shown multiple responses and asked to rank them from best to worst. This ranking process is repeated across many examples, creating a large data set of human preferences. Around 40 trained annotators were involved in this process for this paper, and they are selected carefully through screening to ensure high quality judgments. Interestingly, the agreement between the different annotators is quite high, around 70% or more. This indicates that the people agree on what makes a good response. However, it is also important to note that the model is being aligned to the preference of the specific group of labelers, not all humans, because the labelers are very small set of the whole populations. So while the system captures human feedback, it is still limited by who provides the feedback. Overall, this step converts subjective human judgments into structured data that can be used for training. So coming to the evaluation metrics. So we have built the model, but to evaluate this, how well this model is aligned, the author used both human evaluations and automatic benchmarks. The most important metric is the human preference. Labelers compare this output from different models and choose which one they prefer. This directly measures how useful the model is in the practice. They also use a Likert scale, which is from 1 to 7, to rate the overall quality of the responses. This gives a more detailed measure of the performance. And for truthfulness, they use a benchmark called truthful QA. This checks whether the model provides correct or non-misleading answers, especially for tricky questions. And for safety, they evaluate toxicity using the dataset like real toxicity prompts. This helps measure how often the model generates harmful or inappropriate content. They also test for bias using the standard benchmarks designed to detect unfair or discriminatory outputs. So instead of focusing only on accuracy, the evaluation covers multiple dimensions such as usefulness, truthfulness, safety, and fairness. So this makes the evaluation more aligned with the real world expectations of the AI systems. Now the results. So which are the most important part of the paper. The authors evaluate their model using human preferences, and the result shows a clear improvement over GPT-3. So in most cases, human evaluators preferred the outputs from Instruct GPT over the GPT-3 models. So one of the most surprising finding is that even a much smaller model with only 1.3 billion parameters was preferred over much larger 175 billion parameters GPT-3 model. So this is very important result because it's a challenge. It challenges a common assumptions in machine learning that the bigger models are always better. Here we see that the alignment can actually be more important than the scale of the model. The model also performs better at following instructions. It produces response that are more relevant, more structured, and more consistent with what the user asks. So another key improvement is the reductions in the hallucinations. The model is less likely to make up false information, especially in the tasks where the accuracy is important. It and it also generates more appropriate responses, meaning it avoids harmful or unsafe content more effectively. So overall, these results clearly show that RLHF significantly improves the quality, reliability, and usefulness of the language model. Now, the coming to the key findings. So this slide summarizes the key insights from the paper. The first and the most important takeaway is that alignment is more important than the scale. So instead of simply increasing the model size to like further billions parameters, improving how the model behaves leads to better outcomes. Second, RLHF significantly improves user satisfaction. Since the model is trained directly on the human preferences, it produces output that are people actually find useful and natural. Third, the model becomes more truthful and safer. It reduces hallucination and avoids generating harmful or toxic content. Another important finding is the generalization. Even though the model is trained on the specific prompts, it performs well on the new and unseen tasks. This shows that it has learned a more general concept of following instructions. Finally, these improvements come with minimal performance loss on the traditional NLP benchmarks. So this means we don't have to sacrifice capability to gain the alignment. So overall, RLHF provides a balanced improvement, better behavior without losing the performance. Now the limitations. So now, even though the results are very impressive, the has several limitations. First, the entire process depends heavily on the human labelers. Collecting high quality feedback is very expensive, time consuming, and not easily scalable. Second, the model can inherit bias from the labelers. Since it learns from the human preferences, any bias in those preferences can be reflected in the model's behavior. Another limitation is that a model is aligned to a specific group of people, not all users. Different users may have different expectations, so alignment is not universal. So this is also something called in alignment tax. So this means improving alignment can sometimes reduce performance on certain tasks, especially traditional benchmarks. And finally, the model is still not perfect. It can still make mistakes, fail to follow instruction, or generate incorrect information in some cases. So while concluding, so while RLCF is powerful approach, it is not a complete solution, and there is still room for improvement. Now, to conclude this presentation, this paper shows that a reinforcement learning from human feedback is a very effective way to improve language model. So instead of focusing only on making models larger, the author shows that aligning model with human preferences leads to much better result. And the Instruct GPT model very much outperforms GPT-3 in terms of usefulness, safety, and truthfulness, even though they are significantly smaller in size. So the highlight of this important shift in AI research from scaling model to aligning them. It also shows that human feedback is a very powerful tool for shaping model behavior by incorporating human preferences directly into the training. So we can build systems that are more reliable and user friendly. However, there are still many challenges such as bias, scalability, and ensuring alignment across diverse users. So overall, this paper presents RLHF as a promising direction for building more practical human-centered AI systems in the future. Now we'll see one example. If you can clearly see that on the screen. In this case, the prompt asks the model to create a shopping list from a recipe. So the expected output should be a list of ingredients extracted from the text. So first, we see the labeler demonstration, which is the ideal answer written by a human. It correctly identifies all the ingredients like zucchini, beef, onion, mushroom, cheese, and so on. Now, if we look at the GPT-3 output, we notice something very interesting. Even though its text is fluent, it completely ignores the instruction. So instead of generating a shopping list, it continues the recipe and gives cooking instructions. So these show a key problem. The model is generating text, but it is not actually following the user's intent. In contrast, the Instruct GPT output is much better. It produces a clear and structured list of the ingredients, which is exactly what the prompt is asking for. So this example highlights the main contribution of the paper, not just generating language, but understanding and following instruction very correctly. So this is exactly what RLHF enables, aligning the model's behavior with what the user actually wants. So these are some references from the paper. To conclude, I'll say that the paper shows us what we should ask, like how do we make the model behave better instead of asking how to make the models bigger. So this was my explanation for the paper, training language model to follow instruction using human feedback. I tried my best as per my understanding to explain this paper, and thank you so very much for patiently.
My name is Bhargav and my paper is Chain of Thought Prompting from Pool C. This seminal paper was published by Google Research Brain Team. I would also like to acknowledge the team, my team that helped me put together these slides. Ravi Sharma, Divyansh Rawat, Satyam Pal, and S. Karthikeyan. If I have to summarize this entire presentation in one sentence, it would be this. Researchers found a simple prompting change that unlocked step-by-step reasoning in large language models. We aren't talking about massive architectural overhauls or expensive retraining. We are talking about fundamentally changing how we talk to AI. Let's dive in and see exactly how they did it. Why does this paper matter? The motivation. Let's look at the promise and the problem with scaling language models. We know what scaling gives. Making a model bigger reliably leads to better language fluency, improved few-shot learning, and stronger factual recall. But here is the catch. Scaling alone cannot fix everything. Even massive models stumble on multi-step arithmetic like GSM 8K dataset, common sense inference chains, and symbolic manipulation tasks. This brings us to the core question of the paper. The researchers noticed that even a massive 540 billion parameter model struggles with a grade school math word problem under standard few-shot prompting. They asked, can we fix this without retraining the model? The paper's elegant answer is yes. We just change the way you put in the prompt, not the model. So basically, we have to just change the way we type our queries. Now, let's see what is the difference between the standard prompting versus chain of thought prompting. Under standard prompting, we give the model an exemplar like Roger has 5 balls. He buys 2 cans of 3 each. What is the total? And we simply provide the final answer 11. When we test the model on a new question about a cafeteria with apples, it guesses 27, which is again incorrect. Now let's look at the chain of thought prompting. We take the exact same example, but we expand the answer. 5 balls, 2 times 3 equals 6. More. 5 plus 6 equals 11. Answer is 11. When we give the model the cafeteria test, it replicates that step-by-step logic. 23 minus 20 equals 3 plus 6 equals 9 and arrive at the correct answer of 9. The only difference here is that each two-shot example now includes intermediate reasoning step. There is no fine-tuning, no extra data, and no new model build. Then what exactly is chain of thought? To formalize this, what exactly is a chain of thought? By definition, it is a coherent sequence of natural language reasoning steps that bridges a question and its final answer. Think of it like being back in grade school when your math teacher told you to show your work on the exam, not just like the final answer. You have to show the steps. In the context of few-shot prompting, each example you feed the model now has 3 distinct components. First, the input, which is the question exactly as it is written. Second, chain of thought, which is step-by-step reasoning spelled out in plain English. And third, the output, the concise final answer. The beauty here is efficiency. Only 8 handcrafted examples go into the prompt. Now, these are the most attractive properties of chain of thought prompting. Why is this prompting strategy so powerful? The authors highlight 4 main properties. First, it naturally handles multi-step decomposition. Hard problems are broken into manageable pieces, allowing the model to automatically allocate more computation to harder questions. Second is interpretability. Because the intermediate steps are visible in the plain text, we can see exactly how the model reaches the answer. This makes it incredibly easy to diagnose exactly where the model got wrong. So we would know, like, we could fix that specific step. We could fix that specific part in our prompt so that LLM has a greater understanding. Now, third, broad applicability. Because this relies on natural language reasoning, it extends in principle to any task solvable through verbal reasoning, like math, common sense, or symbolic manipulation. Fourth, it's easy to elicit from off-the-shelf models without retraining. The capability is already latent in large models. Chain of thought simply unlocks it. The take-home message, as you can say, is change the prompt, making it immediately useful for any practitioner. Let's see different examples across task types. Let's see how this broad applicability plays out across different domains. First, for arithmetic. If we ask how many keystrokes it takes to type number 1 through 500, the model actually calculates the character groups step by step rather than just guessing. For common sense tasks, consider the question, would a pear sink in water? The model reasons for a pear's density is approximately 0.6 grams per cubic centimeter, which is less than water, therefore it flows. So the answer is no. Real world knowledge is perfectly woven into step-by-step inference. And for symbolic tasks, like finding the last letters of the word Lady Gaga, the model isolates the Y and the A and explicitly concatenates them. So think of tone of task and asking the model to narrate its thought process aloud. Just like a student standing at the blackboard explaining each step before writing the final answer, or like a teacher explaining how to reach to the final answer. Now, arithmetic reasoning, the benchmarks used. To rigorously test this, the researchers evaluated the models on 5 distinct math word problem datasets. These include GSM-8K, which featured hard pre-response multi-step problem, SWAMP, which tests structural variations at a medium difficulty. Now, as there for diverse problem types, APQUA for algebraic multiple choice questions, and MOPS, an easy medium mix of 1 to multi-step problem. Now, they tested several foundation models, including GPT-3, ranging up to 175 billion parameters, Lambda, Palm up to 540 billion parameters, and UL2 and Codex also. Crucially, the prompt design was minimal. They used one fixed set of 8 handwritten chain of thought exemplars for almost all datasets, with no task-specific tuning performed. Now, these are the arithmetic results on the notoriously difficult GSMA dataset. The chart on the screen highlights a massive drift. The dark blue bar shows that standard prompting on massive Palm 540 billion model achieved only an 18% solve rate. But look at the far right. By simply using 8 chain of thought exemplars, the Palm 540 billion models solve rate rockets up to 57%. That is over a 3x improvement. What makes this truly remarkable is that comparison to the previous state of the art. The fine-tuned GPT-3 model shown in the first bar achieved 55%, but that GPT-3 model was explicitly training on thousands of GMS8K examples with a verifier. Palm 540 billion with chain of thought surpasses it using 0 GSM8K training examples. So it shows how without any retraining, just with understanding how to ask a question, just asking the chain of thought prompting is so powerful. Chain of thought is an emergent ability of the model space. This slide reveals one of the most fascinating findings in modern AI research. Chain of thought is an emergent ability tied directly to the model scale. Take a look at the schematic graph. The x-axis represents the model scale in billions of parameters, and the y-axis is the solve rate. There are three critical observations here. First, for smaller models, those below roughly 10 billion parameters, chain of thought actually hurts performance. Small models produce reasoning that sounds fluent but is logically broken. Second, the large performance gains don't gradually appear. They suddenly unlock only at around 100 billion parameters and above. And third, these gains are largest on the hardest dataset. Easy one step, easy one-step problems show minimal change. The ability to reason is latent in large models, and chain of thought is simply the key that unlocks it without any weight update. Now, arithmetic results, the full picture is here. This is the full summary table of the arithmetic results, giving us comprehensive view across all data. If you track across the Palm 540B row, you see standard prompting versus POP prompting. The leaps are staggering, jumping from 17.9% to 56.9% on GSM 8K and from 79.2% to 93.3% on MOPS. There is one notable exception to be aware of. On the aqua dataset, the Lambda 137 billion model actually drops in performance when using chain of thought. This is a known issue for smaller models struggling with multiple choice algebraic problems. Interesting, the researchers later added an external Python calculator to chain of thought outputs for Palm 540B, which pushed its score to 58.6%. This suggests that sometimes the model fails not because of bad reasoning, but due to simple arithmetic execution error. Now, common sense reasoning. Can chain of thought transfer beyond math? Chain of thought works beautifully for math, but can it transfer to tasks that don't involve numbers? To test this, the team evaluated 5 common sense data sets. These include CSQA for general world knowledge, strategy QA for multi-hop inference, like asking if Aristotle used a laptop, date understanding to infer dates from context clues, sports understanding to judge the possibility of sports sentences, and STACAN, which maps natural language to robotic action sequence. Evaluating common sense is tricky because these are mostly multiple choice format. A model can easily guess the right answer while using completely wrong equation or reasoning. Here, chain of thought is incredibly valuable, not just as a performance booster, but as a diagnostic tool to verify the model actually knows what it's talking about. As before, they only use a handful of manually crafted exemplars. Now let's see the common sense for Palm 540 billion model on these common sense tasks. The dark blue bar represents standard prompting and the light blue bar represents chain of thought. I think we are clear now about that. The highlights are incredible. On strategy QA, chain of thought pushes the model to 77.8%, easily beating the prior best of 69.4%. On sports understanding, the model hit a staggering 95.4%. To put that in perspective, that actually beats an unaided human sports enthusiast who averages about 84% on the star. We see more modest gain on CSQA going up by 1.8 percentage points. This happens because stars that are already near the performance ceiling benefit less from CO2. Finally, on SECAN, CAT provides a massive 10.9% point boost in grounding robot instruction. Let's see the common example reasoning. To truly appreciate what the model is doing, let's look at the text of these reasoning chains. Here is an example of correct reasoning from strategy keyword. Question: was Jackson Pollock trained by Leonardo da Vinci? The model answers: Da Vinci lived in the 15th century, Pollock in 20 and Pollock in the 20th. They could not have overlap. So answer is no. So that is historically accurate and perfectly reasoned. However, we must look at the incorrect reasoning question. Can Harry Potter book a flight on Asiana Airlines? Obviously, the answer should be no. But let's see what the model does. The model reasons Harry Potter is fictional. Fictional characters can do anything. Answer is yes. The ground truth is no. So this is an important teaching now. Fluent, internally consistent chain of thought can still lead to wrong answer. Ensuring the factual correctness of these intermediate steps remains a very active open research problem. Now, symbolic reasoning. There are two toy. Now, this is the final domain tested using the toy task. These are trivial for humans. The first is last letter concatenation. You ask the model to take the last letters of the word like Army, Amy, Brown, and combine them to output YN. Crucially, the model only sees two word names during prompting, but is tested on a 3 and 4 word name. The second is coin flip state tracking. Coin flip state tracking. A coin is heads up. EB flips it. Oswaldo does not. Still heads up. Answer no. Here the exemplars use 2 flippers, but the test uses 3 or 4 flippers. Why use these tasks? Because they act as a direct test of compositional generalization. The model must generalize a chain of thought template to longer, more complex sequences it has never seen before. Symbolic result, length generalization. The result on these symbolic tasks prove exactly how powerful this generalization is. Look at the bars for the out of domain or OOD tasks, which represent the longer sequences. Standard prompting fails completely on the out of domain task, scoring exactly 0%. The model simply cannot extrapolate the pattern without reason. However, with chain of thought, PALM 540 billion achieves near perfect in-domain performance, hitting up to 100% on the coin to task. More importantly, while OOD generalization isn't perfect, it jumps from 0% to 63% and 90.2%. This confirms that chain of thought allows the model to extend a logical reasoning template to longer unseen instances at test time. Once again, models under 100 billion parameters fail even in these in-domain tasks, further confirming them as an emergent ability. Ablation study. What actually drives the game? Being rigorous researchers, the authors conducted an ablation study using Lambda 137 billion model on GSM8K to figure out what actually drives the game. They tested several variants against the standard baseline of 6.5%. Could it just be the model needs to output the math equation? No, the equation only. Variant scored 5.4%. Could it be that model just needs more computation time to generate tokens? They tested variable compute by having the model output filler dollars. That only scored 6.4%. What if the reasoning comes after the answer? Only the full chain of thought sequential reasoning before the answer achieved the 14.3% benchmark. The take home message here is definitive. The sequential natural language reasoning is what drives the game, not isolated equations or extra computation token. Robustness. Does chain of thought depend on the specific prompt? A major concern with prompt engineering is fragility. How sensitive is the model's performance to exactly how you write the exemplar? To test this robustness, they varied the prompts across 4 axes. First, they used 3 completely different annotators with different writing styles. All 3 significantly beat standard prompting. Second, they tried an intentionally concise style, even shorter reasoning chain outperformed the baseline. And third, They use crowd-sourced exemplars, three randomly sampled sets, all worked substantially better. Finally, they scrambled the exemplar order, finding very small standard deviation in almost all the cases. The conclusion is reassuring. Only chain of thought is not a lucky prompt. It reliably outperforms standard prompting across different annotator styles and sets, proving it is a highly robust technique. Now, limitations and open questions in this are, despite the success, the authors are very transparent about the four key limitations. First is philosophical question, like, is the model really reasoning? Like, chain of thought mimics the form of human reasoning perfectly, but whether this constitutes genuine cognitive reasoning remains as an open empirical question. Second, annotation cost scales poorly. Writing on 8 exemplars is cheap, but fine-tuning a model on a chain of thought data would require thousands of examples, which might be cost prohibitive without synthetic generation techniques. Now, third, there is no guarantee of correctness. As we saw with Harry Potter, a plausible sounding chain can be factually wrong, yielding incorrect final answer. Final chain of thought requires very large models. Because it is ineffective below 100 billion parameters, it remains computationally expensive to serve in real-time, low-latency production settings. Now, let's see, but why? Why this paper stands out? To wrap up, let's reflect on why this paper stands out as a landmark in this field. First, its impact is undeniable. It directly sparked an entire subfield of research, leading to techniques like self-consistency, zero-shot chain of thought, tree of thought, and process reward models. Second, it shifted the entire AI paradigm. It proved that prompting can elicit complex compositional reasoning, not just factual recall, shifting the focus from what to fine-tune to what to prompt. By simply adding reasoning steps to few short exemplars, it dramatically lifted the performance across arithmetic, common sense, and symbolic tasks, setting new state-of-the-art records with zero fine-tuning. And it proves the reasoning is a scale-based emergent property. Ultimately, this paper achieved massive impact for conceptual simplicity. It is easy to understand, easy to implement, and yield striking results. If you want to dive deeper into the literature that shaped this presentation, here are the foundational texts and the references. You can look into it. So that was my presentation. Thank you, sir.
Hello, good evening everyone. I am Satyam Pal and today I will be presenting my topic uh, which is global vector for word representation. So now let's start. So these are my team members. So uh, why do we need GloVe? The key idea is GloVe was proposed to capture global statistics information and that CBAO and Skipgram do not use directly. Existing models such as CBAO and Skipgram rely primarily on local context. So actually why we need GLOBE? So answer for this is earlier models like CBAO and Skipgram learn mainly from the nearby words. For example, in a sentence like uh, the cat is sitting on the mat. If the target word is cat, CBAO or Skipgram mainly looks at nearby words like the, is, sitting. So they learn from local context, but they do not directly use the overall statistics of the whole corpus. For example, if across the whole corpus, sentence 1 is ice often appears with solid and stream often appears with gas. Then the then Glove learns that solid is strongly related to ice and gas is strongly related to stream. This helps it understand meaning better. So So this is the whole idea of why we need glow that you can see in this slide. So now intro. Intro word are represented as vectors. Okay, so these vectors helps in many NLP applications. Uh, Word embeddings are evaluated using similarity and analogy tasks. Existing methods are of two types, global and local. So both have limitations. GloVe is proposed to combine their strengths. It uses global co-occurrence statistics to learn better embeddings. So what is similarity here means? Similarity is used actually, it checks if similar words are close or do similar words get similar vectors. Example, vector of car is approximately equal to vector of vehicle. And what uh, word analogy refers to, here we check, in analogy we check whether embeddings capture relationships between words. Example, man is related to king, women is related to queen. So these are the meanings of these two words. So pipeline of uh, pipeline includes text corpus, co-occurrence matrix X, weighted loss, word vectors. So initially we are provided with text corpus, and then we compute co-occurrence matrix that we will see in the next slides, and then we update loss, weighted loss, and then at last we found word vectors. So related works. The two families of word representations are matrix factorization method, that is global, and second one is shallow window based method, that is local. So what is matrix factorization method? These methods are these methods look at the whole corpus statistically together. The simple idea behind the matrix factorization method is they first built a they first built table big table or matrix from the corpus that we was provided we that it is provided in the question. For example, they count how many times cat appears with milk, how many times dog appears with bark, how many times ice appears with solid. Then they reduce this big matrix into smaller vector words. Example of matrix factorization method is LSAHAL COALS calls. Why are they called global? Actually, matrix factorization methods, why they are called global? Because they use information from the entire corpus, not just one sentence or one small window. Earlier methods like Word2Vec and that is skipgram and cbow, they used the concept of window and they proceed according to it. Okay, so now problems with these methods. Very common words like the and of appears with almost every word, so they can affect similarity too much even though they do not give much real meaning. Examples like cat appears with the, dog appears with the, then the model may think cat and dog are similar mainly because of the, but the does not really tells us anything important about their meaning. So frequent words can create noise. Then second method is shallow window based method local, which is local method. These methods learns from nearby words only. The simple idea behind the shallow window based method is, let's take a sentence, the cat drinks milk. If target word is cat, nearby words may be the, drink, milk. So the model learns from these local neighbors. Examples of these shallow based techniques like skipgram, cbow, word2vec. Okay, so that's for it. Now move to the next slide, which is why glove. The repetition flaw in skipgram and cbow. Window based models scan the entire corpus window by window. This fails to take advantage of the vast amount of repetition in the data. So in skipgram and cbow, actually we work with by taking window by window in a sentence we take window and there is one center word and there is neighbor words, and we proceed accordingly. But this fails to take advantage of vast amount of repetition in the data. So glove advantage, it is global log bilinear regression model. It combines the benefits of both families, global statistics and linear substructures. Okay. So now technical improvements over previous models. Handles frequent handle frequent words better. Like glove handles frequent words better than skipgram and cbow. Uses probability ratio for meaning. So it uses probability ratio. Let's see how it uses probability ratio. Okay, so by taking an example we will understand this. Take two words, let's say ice and stream. Now checks how strongly they relate to context words like solid and gas. Suppose probability of solid given ice, it is obviously high, and probability of solid given stream, it is low actually, because solid and ice are related but solid and stream are not that much related. Then the ratio of these two are probability of solid given ice upon probability of solid given stream. This is the ratio. So this is how we compute ratio. Trains on non-zero co-occurrences only, more efficient than window scanning. So this technique is more efficient than window based technique. So now performance summary. uh, Analogy task achieved 75% accuracy on word analogy task. So GloVe achieves 75% accuracy on the analogy task, like king minus man plus women is equal to queen. So these type of analogous task, the accuracy achieved by the GloVe is 75%. Superiority outputs outperforms related models in word similarity task, named entity recognition, capturing both semantics and syntactic regularities. So this is given. Now glove model. Glove learns uh, word vectors from word co-occurrence information. This we will see uh, at last a numerical question. So these things will get clear by solving that question. Okay. So now second point is it uses global statistics from the whole corpus. So what does this mean, global statistics across whole corpus? If corpus if across the whole corpus we have two sentences like ice often appears with solid, stream often appears with gas, then GloVe learns that solid is strongly related to gas, gas is strongly related to stream. This helps it understand meaning better. uh, so the main idea is words with similar context should have related vectors. So this is the main idea. GloVe tries to capture meaning using co-occurrence probabilities. So example like ice appears often with cold, solid, snow. Now GloVe looks at these co-occurrence probability, like probability of solid given ice. This would be high, obviously we know that. So because they are related to each other, it directly uses the word co-occurrence matrix that we will see later. Why ratios? GloVe says that ratios of probability reveal meaning that than raw counts. Example, uh, what actually why we use ratios? GloVe says that just counting words is not enough. Okay, so what is more useful is to compare how strongly one context word is related to one word versus another word. That is why it uses the ratio probability of k given i's, probability of k given stream. So k is equal to context word, probability of k given i's is equal to probability that word k appears near i's, probability of k given stream is probability of word k appears near stream. Okay, so the ratio is probability of k given i's, probability of k given stream. This is the ratio. Basic intuition. Let's understand by a table. GloVe does not rely only on counts. It focuses on ratio of co-occurrence probabilities. These ratios helps identify important semantic differences between words. Probability and ratio. Probability of k given ice. Here k is solid. So solid given ice. Solid is strongly related to ice. Then this entry would be high. And similarly, when we compute probability of gas given ice, which is actually low, so this value will be low as compared to solid. And same for water, probability of water given ice, this would be high, so this value will be high. And similarly for fashion. And that's how we compute the probability ratio table. Now main formula. So main formula is wi transpose wk plus bi plus bk. These are wi and wk, actually these are vectors of target. Wi is vector of target world and wk is vector of context world, and bi bk are basis terms, so which is equal to log of xik. So that we will understand by a numerical. Final objective function, this is the final objective function where we have f of xij, and this term is actually this term, main formula. So actually we are squaring that formula, and taking log x of ik at left hand side, so it will be minus there, so whole square. So this is the final objective formula. Weighting function. So uh, weighting function is in GloVe. This function controls the importance of each co-occurring word pairs. So actually this weighting function is here. This f of xij. This is actually the weighting function. Now let's understand this. Rare co-occurrences should not get too much weights. Very frequent co-occurrences should also not dominate training. Therefore GloVe uses a capped weighting function. So this is f of x is equal to x upon x max to the power alpha, and if x is less than x max, otherwise 1, f of x value will be 1 if x is not less than x max. So this we will understand by numerical. So now let's understand this graph. Weighting function f, and standard value of alpha in the paper is 3 by 4. So for small xi, weight increases gradually. So here you can see this weight increases gradually, and xi is here actually small. When xi grows or it becomes large, then after x max the weight becomes constant at 1. So this is, here you can see, this is the standard graph which was used in which is used in paper of GloVe. So now relationships to other models. uh, so here, connecting GloVes to skipgram. How is GloVe related to Word2Vec? So GloVe and Word2Vec are related because both learn word embeddings from co-occurrence information. Skipgram in Word2Vec predicts nearby words using a softmax probability function, but this is expensive because softmax needs to consider the whole vocabulary, and the model trains by scanning many small windows. GloVe keeps the small goal of learning meaningful vectors, but instead of predicting word by word, it uses the global co-occurrence counts of the corpus. So this is the idea behind connecting globes to the skipgram. So now let's move the transformation. The transformation actually replace cross entropy with least square, remove costly softmax normalization, use log co-occurrence counts for stability. GloVe GloVe cost function is like summation of ij xi wi transpose wj minus log xi ka whole square. This is what we see earlier. So uh, actually we can discuss this term, replace cross entropy with least squares. So in skipgram, and the model tries to match probability using cross entropy loss. But actually in GloVe says instead of comparing full probability distribution, we can use a simpler error measure, least square. That means calculate prediction, compare it with large value, square the difference, Example, if target value is 3 and prediction is 2.5, then the error is 3 minus 2.5 ka whole square, which is equal to 0.25. This is easy to optimize. Simple meaning, GloVe uses a simpler loss function than skipgram. Okay, this is computational complexity, depends on non-zero entries. Non-zero, and that is if we have dense matrix in the co-occurrence matrix, dense values in the co-occurrence matrix. Worst case, big O of v to the power 2. Practical case, matrix is sparse. In practical case, our matrix will be sparse. actually complexity is about big O of c to the power 0.8, efficient for large corpora. So GloVe is actually efficient for large corpus, and it is not that much efficient for small corpus. Evaluation method: GloVe tested on analogy, similarity, and named entity recognition. Main evaluation is analogy task. 19,544 semantic and syntactic equations. The answer is found using vector arithmetic. So this is the equation by which we will form our answer. The closest word is selected using cosine similarity. So actually, for the closest word selecting, we use cosine similarity, and it is its main purpose is analogy task. Okay. So results based on analogy task improves with larger corpora, and as we increase corpus size, then our results will also get increased. Best accuracy is 75% when we was using 42 billion corpus, a word with 42 billions corpus with 42 billion words. Similarity results strong result on similarity benchmark. 42 billion model perform best, outperforms the several baselines. Named entity recognition results strong performance on NER, based on near best F1 scores. So these are something which is also discussed in paper. Table for results. So these are the standard results which was given in the paper. So SVD on 6 SVD model SVD on 6 billion 35.5, WS 353 MC 31 35.1. These are taken from the paper. Actually the larger corpus improves performance. Syntactic accuracy increase steadily. Best results come from the common crawl 42 billion corpus size. Comparison with Word2Vec. GloVe was compared with CBOW and skipgram. Under the same setup, GloVe performs better. Under the same setup, GloVe performs better. GloVe actually, when we compare GloVe with CBOW and skipgram, and then results are in favor of GloVe. Actually, we can see it here. GloVe versus CBOW. So uh, orange line, this is showing GloVe, and purple line, this is showing CBOW. So on x-axis we have training progress, on and on y-axis we have accuracy. Okay, what it shows is GloVe starts improving quickly, and accu- its accuracy keeps rising and reaches around 71%. So you can see it here by orange or red line. CBOW improves at first. CBOW improves at first, uh, but then stays lower and even drop slightly. So you can see it here by blue line or purple line. It's improves first, then start decreasing, and this comes here. So the same training effort. So for the same training effort, GloVe performs better than CBOW. Now comes to GloVe versus skipgram. That you can say GloVe is performing better than skipgram, and skipgram starts in starting works fine, but it's not as much good as GloVe is showing the accuracy. So this is how you can check it here, that GloVe are around 72% achieving around 72% accuracy, and it is achieving around 68 plus something, almost 68. So this is how GloVe versus gram graphs is showing. Conclusion: word embeddings can be learned by count based and prediction based methods. Both approaches are closely related. GloVe combines global statistics with linear semantic structures. It performs strongly on analogy, similarity, and NER, named entity recognition, but it gives 75% accuracy on analogy, which is the max. So now let's do example. So actually, take one very small corpus. Let's say corpus have two sentences: ice is solid, stream is gas. So step one is convert it in vocabulary. So ice is solid, stream, gas, these are the unique words. So we form a vocabulary. Context window, let's say we are taking one. So So mainly intermediate neighbors count. So actually we are only counting intermediate neighbors because our context window size is 1. Step 2, build co-occurrence counts. For sentence 1, ice is solid. So for target word ice, context word is just next near neighbor. For is, there are two next near neighbors, ice and solid. So for target word is, context are ice and solid. For solid, context is. Same for gas. From same for stream is gas from sentence 2. For target word stream, there is only context word is. For target word is, there is two context word which is stream and gas. And for target word gas, there is only one context word which is this one. So step 3, co-occurrence matrix. So actually what is co-occurrence matrix? Here we are given target words and here we are given context words. So ice, let's check in the corpus. Ice are appear together, no, so this value will be no. Ice is, so ice is appeared together, so this value will be 1. Similarly for ice solid, this is ice solid, no, ice solid solid comes together, so this is 0. Then for gas this is 0. Similarly for ice, I is ice, which is, if ice is 1, then is ice is also 1. And similarly we will calculate whole this co-occurrence matrix. And the important thing is GloVe learns from these counts which are in co-occurrence matrix. So GloVe learns from these counts. Step 4, pick one word pair to train on. Pick one word pair to train on. Take the pair target word I. So target word I is equal to ice, context word is represented by j, which is equal to is. So from the matrix, value of i's comma is pair, value of pair i's comma is i's comma is 1. So this value will be taken from the co-occurrence matrix, which is equal to 1. So GloVe tries to make this GloVe equation. So we will calculate this GloVe equation now. This is core GloVe equation. Since x of i's comma is equal to 1, so log of x ij, which is equal to log of 1, which is equal to 0. So put this 0 in the equation, so we will get this w ice transpose. W is because value of I is representing ice and j is representing is, because these are what, I is target word and j is context word. So this is equal to 0. So now initialize the parameter. We randomly initialize the parameters, which is w I is equal to 0.50, w is equal to 0.20, b I is equal to 0.10. These are biases, b of i's and b of is. These are biases of i's and is. These are the trainable parameters. Actually, we will compute by the gradient descent algorithm, and we will improve these parameters. Compute prediction. Compute prediction. So first compute dot product. What dot product? We have to compute this equation wj plus bi plus bj, and log of xi we will take at left hand side, and this will come as minus. So we will compute these equation. W is value 0.5, w is value 0.2, so 0.10. This is the result. Now add biases in it. So because this is given in the question, bi plus bj, so bi value 0.10, b of is equal to 0.05. So we will add these values in this equation. So 0.10, 0.11, and this is the bias of b is, so which comes as 0.015. So y at is equal to 0.15. So actually this term is comes as 0.15. So now log of x is comma is, which is equal to log 1, which is equal to 0. Now we will subtract from y hat. This is our error, e is equal to y hat minus log of xij, which is equal to 0.15 minus 0, which is equal to 0.15. Now weighting function. GloVe uses weighted least square. J is equal to fxij wij, and this is basically that equation. This is basically that is e which we already calculated, error function. So we are only doing here is e to the power 2. So this term we already calculated, just we need to here is square this term. So we are going to square this. So what is f of x ij? F of x is equal to x given x max to the power alpha when x is less than x max, otherwise it is 1. So standard values of x max comma alpha is this, which we have taken it from paper. So for RPR x is equal to 1. So for RPR x is equal to 1, that means x is less than x max. So we will f of x is equal to x upon x max to the power alpha. So f of 1 is equal to 1 upon 1 upon 100 to the power 3 by 4. So which comes as 0.0316. So we will put this equation here, put this value here, and there is this term which is e. So 0.15 we will plug in here, and we will do square of that term. So f1 is equal to 0.0316. Now compute loss for this pair j ij is equal to f of xij dot e to the power square. So just put 0.0316 into 0.15 to the power whole square. This will comes as 0.000711. So now next step is one gradient update step. Now we update parameters so prediction gets closer to target. So this is our main step. For one pair define e, that is error is equal to that we already calculated, that we already calculated it. So it comes as 0.15, and jij is equal to f of, this is the whole equation which we calculated here, 0.00711. So now take derivative with respect to wi. So here we are going to tell we are going to derivative with respect to w is w i's, b of is, b of i's. So these for computing gradient descent and improving our weights. So actually we are taking derivative of function jij. So when we take derivative of j with respect to wi, this will come as 2 times of f of x into e into wj. So f is equal to 0.0316, which we calculated earlier, and e is also 0.15, wj is 0.20, which is given, which we take randomly in the starting. So del j upon del wi i's is equal to, by plugging in these values in this equation, then we will get 0.01896. Similarly for del j upon del w is equal to 2FEWI's. So actually here not WI's, it is actually WS. So WS value is so we will compute this whole term by plug in values. So we will get 0.00474. Okay, now bias gradient del j upon del b i's, which is equal to, we are taking derivative with respect to bias of i's. So we will got 2 times of fe. So plug these values and we will get 0.00948. Similarly for bias of is, so we will get this same value. Update with learning rate. Now apply gradient descent. Weight new is equal to weight old minus eta times del l upon del j upon del weight. So wi's comma wi's of wi's new is equal to wi's old minus eta, which is equal to 0.1 into del j upon del wi's, so which was 0.001896. So after computing this will come as this value. Similarly for w is new is equal to w old new minus eta into uh, that gradient which we computed. So put this value here and we will got this. Similarly for bias terms also, so we will got this and this. Check new prediction. Now we compute wi's comma wi's new, w is new is equal to, multiply those final values here. So we will got 0.099668. So add biases values, these are the biases values. So what we will got is 0.14772. We are doing multiplication of w is and adding b of his values, and we are getting this. So old prediction was 0.15, new prediction is 0.14, target is 0. So actually we are getting closer to 0 from the earlier one, old prediction. And new prediction is somewhat closer to 0. So the prediction moves slightly closer to target. That is how GloVe learns step by step. Thank you. That is all for the GloVe paper.
everyone, I'm S. Karthikeyan. I'll be presenting the paper Efficient Estimation of Word Representation in Vector Space. Let me quickly give you an overview of what this paper is about. The main goal of this paper is to learn better representation of words, what we call word embeddings, using very large amount of text data. To do this, the authors propose two new model architectures. Instead of focusing only on improving accuracy like many earlier approaches, they also care about efficiency, how fast and computationally cheap the models are. They trained these models on a massive dataset of about 1.6 billion words, which is quite significant. Despite the scale, the models are surprisingly fast. They can be trained in less than a day. Now, in terms of performance, the results are strong. The models outperform previous neural network based methods on word similarity tasks, meaning they capture relationship between words more efficiently. And importantly, they work well for both syntactic relationship like grammar and semantic relationship like meaning. So overall, the key takeaway is that this paper achieves better results while also being much more efficient, which is a big step forward. Before going further, let's quickly understand what word embeddings are. In simple terms, word embeddings are a way to represent words as vectors, basically a list of numbers in a continuous space. Unlike traditional relationship like one-hot encoding, where words are treated as completely independent, embedding capture relationship between words. This means that similar words like king and queen or cat and dog end up having similar vector representation. What's even more interesting is that these vectors can capture deeper relationships. For example, certain pattern like gender or tense can be represented as directions in this space. These embeddings are learned automatically from large amount of text data, which allows model to understand language more effectively. And because of this, word embeddings have become a fundamental building block in many NLP applications. Now, let's look at what the authors are actually trying to achieve in this work. First, their main goal is to learn high quality word vectors, but not on a small dataset. They specially they specifically focus on scaling this up to billion of words and very large vocabularies, which was not feasible with earlier models. In previous approaches, models were typically limited to a few hundred million words and relatively small vector sizes. So, one of the key motivation here is to push beyond those limits. Another important goal is not just to group similar words together, but to capture different type of similarities. For example, words can be similar in a meaning, or they can share grammatical patterns like similar endings in certain languages. But what really interesting is that these word vectors can capture deeper relationship. The authors highlight this with a famous example. If you can take a vector for king, subtract man and add women, you end up very close to queen. So the model is not just learning words, it's learning relationship between them. Because of this, the authors aim to design models that preserve these linear relationships in a vector space. Finally, they also focus on two practical aspects: improving accuracy in these relationships and understanding how performance depends on factors like vector size and amount of training data. So overall, the goal is not just better words representation, but scalable, efficient model that capture meaningful linguistic structure. Before this paper, there were already quite a bit of work on representing words as continuous vectors. One of the earlier influential approaches used feed-forward neural network to learn both the vector representation and language model at the same time. While effective, while effective, these models were quite complex and computationally heavy. Later, researchers proposed a slightly different idea. First, learn the word vectors using simpler neural network, and then use those vectors separately to train a language model. This made the process more flexible and somewhat easier to manage. Over time, it became clear that these words vector were extremely useful. They could improve a wide range of NLP tasks like language modeling, translation, and text classification. However, there was still a major limitation. Most of these models require a lot of computational resources and time to train, especially on large datasets. So, this is where the current paper positions itself. So, it builds on the simpler architecture from earlier work but focuses specifically on making the learning process much more efficient and scalable without sacrificing the performance. Now, let's move to how the paper approaches model design. There are several existing models to learn word representations, such as LSA and LDA. They were quite popular earlier, specifically for capturing topics and general patterns in English in text. However, the authors choose to focus on neural network based models. The reason is that these models are much better at capturing what we call linear relationship between words. Things like analogies and structured similarities. Another important issue is scalability. For example, methods like LDA become very computationally expensive when we apply them to really large datasets. So instead of just focusing on accuracy, the authors explicitly think in terms of trade-off between accuracy and computational cost. To formalize this, they define the training complexity of a model in terms of three main factors: the number of training epochs, the size of dataset, and the cost of the model itself. They show that the total computation grows with all three of these factors, which makes efficiency a critical concern when working with a billion of words. Finally, all the models in this paper are trained using standard techniques like stochastic gradient descent and backpropagation. So the key idea here is design models that are not just accurate but also efficient enough to scale to very large datasets. To make this more concent- to make this more concrete, the authors express training cost as a simple formula. Here, E is the number of times we go through the dataset, T is the number of words, and Q represent how complex the model is. Since T can be extremely large, up to billions of words, even small improvement in Q can lead to huge saving in computational time. So the goal of the paper is to really reduce this model cost while still keeping the representations accurate. The slide shows This slide shows the traditional feed-forward neural network language model, which is paper built upon. The model takes a fixed number of previous words, let's say n words, as input. Each word is represented using one hot encoding, meaning only one position is active in a large vocabulary sized vector. These inputs are then mapped into a projection layer, which is essentially where the word embeddings live. This step is relatively efficient because only a few inputs are active at a time. From there, the model passes through a hidden layer which learns patterns and relationship between the input words. Finally, the output layer predicts the probability of next word. But here where the problem arises. The output layer has to consider the entire vocabulary, which can be extremely large. So even though the model is effective, it becomes computationally expensive, especially when scaling to millions of words. To understand why this model is slow, we can look at its computational cost. There are three main components, but the most expensive part comes from the hidden to output layer, which depends on the vocabulary size. Since the vocabulary size can be huge, this term dominates the total computation, making training very slow. To address this issue, the authors used a technique called hierarchical softmax. Instead of predicting over the entire vocabulary directly, they organize words into binary tree structure. Each word is represented as a path in this tree. They specifically use Huffman tree, where more frequent words get shorter paths. This means fewer computation for common words. As a result, the cost reduces from being computational to the vocabulary size to roughly the logarithm of vocabulary size, which is a big improvement. However, even with this optimization, a large part of computation still comes from a hidden layer, and this is exactly what motivates the author to later propose even simpler architecture without hidden layers. To overcome some limitations of this feed-forward model, researchers introduced recurrent neural network-based language models. One major issue with the previous model was that we had to fix the number of context words in advance. In contrast, RNNs don't have this restriction. The key idea here is recurrence. The hidden layer is connected to itself across time. This means the model can carry information from previous words forward, effectively giving it a form of short-term memory. So instead of looking at just fixed windows of words, the model can, in principle, use information from much longer sequences. Because of this, RNNs are able to capture more complex patterns in language compared to shallow feed-forward networks. Now, if we look at the computational cost, we again see two main components. The output layer cost can be reduced using hierarchical softmax, just like before. However, the main bottleneck now comes from hidden to hidden connections, the recurrent part, which scales with the square of hidden layer size. So while RNN are more powerful in terms of capturing pattern, they are quite expensive to train, especially on large datasets. And this again motivates the need for simpler and more efficient architecture with the paper, which the paper proposes next. Up to this point, we have seen that existing models, whether feed forward or recurrent, are powerful but computationally expensive. The authors make a key observation here. Most of the computational cost actually comes from non-linear hidden layer. So instead of trying to make these complex models more efficient, they take a different approach. They simplify the model itself. The idea is to remove or reduce the role of the hidden layer, even if it means the model might be slightly less expressive. The trade-off is that we can now train on much larger dataset more efficiently. They build on an earlier idea where training is done in two steps. First, you learn word embeddings using simple model. Then, if needed, you can use these embeddings in a more complex language model. In this paper, the focus is mainly on first step, learning high quality word vectors effectively. So overall, this section introduces a shift in thinking. Instead of maximizing complexity for accuracy, the goal is to find a simpler model that scales better while still capturing useful relationships. The first model proposed in this paper is called Continuous Bag of Words or CBA. The main idea is quite simple. We try to predict a word based on this surrounding based on its surrounding context. So instead of predicting the next words like traditional language model, here we use both past and future words to predict the current word. Now, the key design choice is that the model removes the hidden layer completely. This makes the model much simpler and significantly faster. And the context words are projected into their vector representation, and then these vectors are averaged. That's why it's called a bag of words model. In other in other in order of words doesn't matter, only which the words are present. Even though this might seem like a simplification, it turns out to work very well in practice. So overall, CBOW trades a bit of complexity for a big gain in efficiency while still learning meaningful word representations. If we look at computational cost, we can see why CBOW is efficient. Since there is no hidden layer, we avoid the most expensive part of traditional neural networks. The remaining cost comes from combining the input word vectors and computing the output probabilities, which is further optimized using hierarchical softmax. So compared to earlier models, CBOW is much faster and can easily scale to very large datasets. The second model is called continuous skip-gram model. It is quite similar to CBOW, but the direction is reversed. Instead of using context to predict a word, here we use the current word to predict its surrounding context. So for a given word, the model tries to predict multiple nearby words in the sentence, both before and after it. One interesting detail is that the model considers range of context words. A larger range generally improves the quality of word vectors because the model sees more relationship. However, not all context words are equally important. Words that are farther away are usually less related, so the model gives them less importance by sampling them less frequently during training. So in terms, skipgram focuses on learning word relationship by predicting context from a single word. In terms of computation, the complexity now depends on context window size, which is denoted by C. For each word, the model makes multiple predictions, one of the each surrounding word. So naturally, as we increase the window size, the computational cost also increases. But this comes with a benefit. Larger context helps the model learn richer word relationship. So there is again a trade-off here between computational efficiency and representational quality. In practice, the authors use a reasonably large window size to balance both aspects. Let's use this diagram to clearly understand the difference between CBOW and skipgram, starting with the left side, which is the CBOW model. Here, we take multiple context words. For example, the words before and after a target word. You can see them on the left: WT minus 2, WT minus 1, WT plus 1 and WT plus 2. All of these words are passed into model and combined typically by averaging their vectors representations. This is why you see this sum block in the projection layer. This combined representation is then used to predict the center word, which is WT. So in simple terms, CBOW is learning to predict a word based on its surrounding context. Now, if we look at the right side, this is the skipgram model. Here, the process is reversed. We start with a single input word, WT, in the middle. Instead of combining multiple inputs, we now use this one word to predict several surrounding words. So the model tries to predict WT minus 1, WT minus 2, WT plus 1 and WT plus 2 individually. This is why you see multiple arrows going outward from the projection layer to different output words. So visually, you can think of it like this: CBOW is many inputs to one input and skipgram is one input to many output. And that simple difference leads to different learning behavior and trade-offs between speed and accuracy. One of the most fascinating things about word embedding is especially the one learned by CBOW and skipgram is that they capture relationship in a very structured way. For example, If we take the vector for king, subtract man and add women, we get something very close to queen as discussed before. This shows that model has actually learned the concept of gender as a direction in vector space. Similarly, we can see geographic relationship. If we take Paris, subtract France and add Italy, we get Rome. It also works for grammar. For example, the relationship between walk and walking is similar to swim and swimming. And even simple similarities like big and large or small and tiny are captured because these words appear in similar context. So these embeddings are not just storing words, they are actually encoding meaning relationship between them. To conclude this paper, this paper shows that we don't necessarily need more very complex neural network to learn high quality word representation. The authors demonstrate that simpler model like CBOW and skipgram can actually perform very well while being much more computationally efficient. Because this efficiency because of this efficiency, these models can scale to extremely large dataset, even up to trillions of words, which was not practical with earlier approaches. In terms of performance, the learned word vectors achieve strong results on both syntactic and semantic tasks, and in some cases outperform previous state-of-art methods. Another important point that in that these words vector are not just theoretical. They are highly useful in real-world NLP applications like sentiment analysis, paraphrase detection, and even tasks like knowledge base completion. So overall, the key takeaway is that these words make word representation learning both scalable and practical, and it has had a major impact on modern NLP systems. In short, this paper shows that simple, well-designed model can go long way when combined with a large-scale data set. These are the references what paper has used. They have referred. I have listed down some of them. So, yeah, thank.
Greetings, this is Divyan Shrawat from MTech Artificial Intelligence. Today I am going to present a research paper term titled as Term Weighing Approaches in Automatic Text Retrieving by Gerard Salton and Christopher Berkeley. So this paper is very important because it explains how search system decide which document are relevant in to a query. The key focus is on how assigning the key focus is on how assigning importance or weight to word can significantly improve the retrieval performance. So so what this paper is about. This paper focus on improving the document retrieval. Uh, why? So the question comes in mind is why this is needed. So because in earlier systems, it was not possible to effectively distinguish between relevant and irrelevant documents. So the authors introduced the idea of term weighing and assigning importance to the words. The main goal is to find the best way to represent the document and assigning the weights so that the retrieval becomes more accurate. So the origin of information retrieval was begun in early 1950s with Loon's idea. The problem at that time was how to search a large collection of document efficiently. So the solution was to represent the document using important words called terms. This idea is still used in today's search engines. So document representation. Um, so what this document represents is a document is represented as a vector of terms, and why was it needed? Because computers cannot understand the full text directly, so we convert into a structured form. The use of vector representation allow us to apply mathematical operations. So this forms a basic of vector space model. If we want to know that how a document is represented, then this is the document vector, where t1, t2, t3 are vectors of are term vectors. So now query representation. So what the query representation is, similar like a document, similarly like document is represented similar in that way, query are also represented as vectors. So why? Because so question arises, why? Because both query and document must be in the same format to compare them. This ensures that similarity calculation can be applied effectively. This is the way in which query is represented. So weighted representation. Now this is the important improvement in weighing. Why was this introduced? Because all the words were equally important. All the words were equally important, and like for example, common words like the are not useful, so we assign weight to represent importance. Mm. So this allow better ranking of each document. So WDK represent the weight of document, WQK represent weight of a query. So weighing problem. Initially binary weighing was used. Initially binary weighing was used, but why was it insufficient? Because it only checked whether a term is present or not. Like it gives 1 for if term is present, 0 if term is not present. So also it ignores how important or frequent a term is. So it cannot differentiate between importance and important and unimportant word, and this lead to poor retrieval results. Now similarity function. uh, to retrieve a document, we need a way to compare uh, them with queries. That is why similarity functions were introduced. They calculate how close a document is to a query. High similarity means higher relevance, and they are very closely related. So the similarity function is formula for similarity is this, where Q is query and D is document, and the summation of weight of query K and weight of dot product with weight with document D. Now cosine similarity. So however, simple similarity has a problem. Longer documents may get higher score. So cosine similarity was introduced. It normalizes vectors and removes the length bias. This ensures the fair competition between documents. So formula for cosine similarity is this, where QK represent the query K and D represent the kth document. So now move to a question where so at this point the paper raises an important design question. So which term should we select? So how should we assign the weights? And these questions guide the rest of the paper. So the simple first let's move to the simple method, like single term indexing. So it uses the individual word as a feature. It's simple and efficient also, works consistently across dataset, and is preferred over complex method, because because it works well, and there is a reason to there is a reason to implement this method because of its simplicity. Now, complex method. Researchers try a complex method like phrases and thesaurus. But why? To capture the deep meanings. However, these methods were difficult to implement and inconsistent, so they were not reliable. Now the question is which term to select. So the complex method, complex method where phrases are complex method which is consist of phrases and knowledge based, uh, but is not reliable. So single term indexing is best. That is a simple method, and hence we get answer to our first question. Now, term frequency. So TF means number of occurrences of terms in a document. So, what it measures? So it measures how often a term appears in a document, and it indicate the importance within that document. Mm, and also, if there is a higher TF, that means term is more representative, uh, and it also help to improve recall. That is more matching terms. So different TF variant exist, which is binary, raw, and normalized also. Now, IDF. Inverse document frequency. So IDF measures how rare a word is across a document. And why was it introduced? Because common words are not useful for distinguishing between documents. So its use is to improve the precision by emphasizing real words. So one more thing is that uh, formula for IDF is log n by capital N by n, where n is capital N is number of document and number of terms is number of particular term is n, mm, having the that word. So if we combine TF-IDF, so TF, why do we need to combine TF and IDF? So because we need both local and global importance. So its use is to assign high weight to words that are frequent in a document but rare overall. So this is most important concept in our paper. Uh, Now, how to assign weights? We can use TF, we can use IDF, and then combine TF and IDF, and then apply normalization. And this is the answer to our second question. Now, why normalization? So, uh, first is we will start with cosine normalization. So, what is normalization? Normalization was introduced to solve the problem of length bias, and if we go to if we go to this cosine normalization, so it adjusts weight based on length factors and prevent document from prevent document from dominating. It ensures the fair competition, fair comparison, and essential in cosine similarities. And the formula for cosine normalization is this: w dash equals to w by root summation of w square, where w is the weight. Now the question comes is how to improve accuracy. So first is use TF-IDF plus normalization. So it will improve accuracy, it will enhance the query weighing, avoid binary weighing, and hence we got our answer to the third question also. So now normalized TF.
where to use this. TF means frequency of a term in document, and max TF means maximum term frequency in that document. Now if we compare if we compare if we have want to see the formula for if we can see the formula for weighing also, mm, and that is normalized TF also. So this is the formula where n equals to 0.5 plus 0.5 into TF upon maximum of term frequency. So it represent it only says that whether uh, term is present or absent. So also this raw TF count only frequency, and normalized TF scales the value between 0.5 and 1, and this reduces the dominance of very frequent terms. Now probabilistic IDF. So this is the formula for probabilistic IDF. So why was it introduced? To give a probabilistic interpretation of a term importance. So its main use is mainly in advanced models. So if we talk about the formula, is IDF equals to log capital N minus n small n upon n, where capital N is number of terms, and number of terms in a document, and small n represent the number of that particular term in that document. So now recall, and let's move to recall and precision. So uh, recall means completeness, and precision means accuracy. So trade-off between them, and this is the trade-off between them. High recall yield more result, and high precision yield more correct results. How to balance, so the question is that how to balance recall and precision. So what TF does, it improves the recall, and what IDF does, it improves the precision. So if you combine them together, they will balance, and this was a answer to our fourth question. So there is a experimental setup. So first is why experiment were conducted. This experiment is derived from the paper that these slides are based upon. So so the question is like why experiment were conducted. So first is we wanted to evaluate the effectiveness of different term weighing schemes, and also to find which combination gives us the best retrieval performance, and to compare simple versus complex weighing approaches. So what was our setup? So setup was like there were 6 document collection, and the collection were of different sizes, domain, and have different query types. So there were 1800 weighing combinations were tested, and which were reduced to 287 distinct systems. So what was our evaluation method? So performance was measured using precision at different recall levels, and document were ranked based on similarities. So what was the result that they got? So the key result were TF-IDF with normalization gives the best performance, which we discussed earlier also. Systems using both TF and IDF outperform everyone. So result were consistent. Also the result were consistent across multiple data sets. So what we can interpret from this? So we can interpret that proper term weighing is critical. Combining local TF and global IDF is importance is if global importance is effective. So global importance is basically IDF, and normalization ensures the fair competition. So now we have some special cases, which is NLP dataset. So spatial observation in NLP collection. So queries are extremely short. So each term appears only once. So term frequency becomes useful. Effect on weighing. So TF has limited impact. Binary weighing performs completely better, and IDF is still useful. So what is the final recommendation? So recommended weighing scheme is for document TFC, where TF-IDF plus cosine normalization is there, and NFC normalized TF plus IDF plus normalization. And for queries, this was for documents, and for queries we have NFX normalized TF plus IDF, TFX raw TF plus IDF, and BFX, that is binary TF plus IDF. So now moving on to real world application of TF-IDF, we can use it in search engines, recommendation systems, and chatbot or NLP. Now, so what is our conclusion? So so let's move here on the. So conclusion was like term weighing is essential and essential for effective information retrieval, and normalization improve fair competition across documents length, and simple single term indexing outperforms complex method. Performance depends on dataset, query, and characteristic, and the main is TF-IDF provides the best balance for of recall and precision. So we have so these were all the concepts that was used in the paper. So I have a bit of practical implementation here that I will run in Colab. So here so I have what is being done here is we have first imported a required library like TF-IDF vectorizer and cosine similarity from feature extraction and metric pairwise. Then we have defined a document, what our document is, will what our document will look like. So if so this is our document where there are three documents, D1, D2, D3, where we have like first document is machine learning is powerful, deep learning is part of machine learning, and then third document is artificial intelligence and machine learning. So now let's and this is the defined query where query is machine learning. Then here we are converting in that documents into TF-IDF vectors, and these are separate vectors, document vectors and query vectors, represented as a metric. So now this is our printing section, what we are printing, and here also we will print the most relevant document. So let's run it. So this is the output we got. So uh, document what this output shows is document 1 has a similarity score of 0.5014, and document 2 has 0.4959, and document 3 has 0.3920. So document 1 has highest score. This means document 1 is the most relevant to the query machine learning. So in simple words, the system compares weighted term vectors and select the document within the highest similarity, which is exact the approach described in the research paper. So this demonstrates how TF-IDF and cosine similarity work together and rank the document based on relevance.